We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello students, my name is Khushbu Mehta. I am working as Assistant Professor in SNPIT and RC UMRAKH. I am going to deliver a brief lecture on Gibbs-Duhem equation, which is broadly used as calculation of partial properties for binary mixtures. So what is Gibbs-Duhem equation? In mixture, the change in partial molar properties of components with compositions that means mole fractions X or Y at constant temperature and pressure can be explained well by the Gibbs-Duhem equation. So by Gibbs-Duhem equation we can measure the change in partial molar property of the components with composition. That means if we change the composition of the mixture, there is a change in the partial molar properties of the mixture. So we can measure that change at constant temperature and pressure by the Gibbs-Duhem equation. The partial molar properties of component in a mixture are related to one another by most useful equation in thermodynamics, the Gibbs-Duhem equation. So basically it gives the relationship between the partial molar property of the components in a mixture. Since the free energy of the system in a state is a state function, it depends upon temperature, pressure and volume. Now if the system is of fixed composition, then it can be written as G is equal to function of pressure and temperature. So if we fix the composition, Gibbs free energy will depend only on pressure and temperature. But in case of an open system where the quantities of the component vary, the Gibbs free energy will depend upon the quantities of the components. For a component system, the free energy G is a function of temperature, pressure and quantities of the component. So basically if we take an open system, that time Gibbs free energy will depend upon temperature, pressure and the quantity, right? Deriving the Gibbs-Duhem equation from thermodynamic state equation is very easy. The Gibbs free energy G at equilibrium can be expressed in terms of thermodynamics as the Gibbs free energy of the system can be expressed as G is the function of pressure, temperature and Ni and Nj, which is the mole fractions, mole number of the particular component I and J. So basically Gibbs free energy will depend upon pressure, temperature and the mole numbers of the particular components. If the variables undergo the change, the total differentiation will be here dG is equal to del J upon del T. At that time pressure and other composition of the component will be remain constant into dt, because here we write down the equation in terms of dg, so we multiply dt at the left hand side, at the right hand side. So here the first term, now second term, we take the derivative, partial derivative with respect to pressure. Means if we change the pressure, we account the change in the Gibbs free energy and write that in terms of del G by del P at constant temperature and mole number into dP plus del G into del Ni. That means the change in the Gibbs free energy with respect to component, with respect to mole number of the component I. So at that time pressure, temperature and other mole number of the component will be remain constant. same as for Nj. So at that temperature and mole number except Nj will remain constant. Here dG is equal to, we have written in terms of entropy and volume equation, minus SdT plus VdP plus summation of I mu I dNi. Now, if we take in consideration the condition that temperature and pressure is constant, then the terms, above terms will be cancelled out, and only remaining terms will be summation of mu I into dNi. Why we write mu I? Mu I, that means chemical potential. So change in the Gibbs free energy with respect to mole number. That means the partial molar Gibbs free energy for the particular component is equal to the chemical potential of that particular component. So we replace that partial molar Gibbs free energy, that means del J upon del Ni, at constant temperature and pressure and other mole numbers with chemical potential of that particular component. So put the summation sign to take in consideration to the n number of moles. So summation of I mu I into dNi is equal to dG at constant pressure and temperature. Now dG, so here is that equation. Now integration the above equation, we get free energy at constant pressure and temperature is equal to summation of mu I into Ni. So here we take the integration and we get the equation in terms of Gibbs free energy. So G is equal to summation of mu I into Ni. Now if we consider this equation and then take the total derivative, so you can see here mu I into Ni is in multiplication. So we have to take derivative in terms of both. So our final equation will become dG at constant pressure and temperature is equal to mu I dNi plus mu 2 dN2 plus mu 3 dN3. So we have relieved the summation and put in terms of numbers 1, 2, 3 up to n numbers. And here first term you can see in the derivative equation is we had take the derivative in terms of mole numbers, and in second terms we have take the derivative with respect to chemical potential of the particular component. So second term is d mu I into Ni plus d mu 2 into N2 plus d mu 3 into N3 and go on up to n numbers. So that is equation 3. Now we subtracting equation 1 from equation 3. So what is equation 1? Here you can say this is the equation 1. dJ is equal to PT is equal to summation of mu I into dNi, and here is the equation 3. So you can see that left hand side terms are equal. So it will be, if we subtracting, it will be 0, and if we relieve this summation here, so it will become mu 1 dN1 plus mu 2 dN2 mu 3 dN3 up to n numbers. So it will be cancelled out here. So we got only term d mu 1 into N1 plus d mu 2 into N2 plus d mu 3 into N3 up to n numbers is equal to 0. So if we write in terms of summation of I d mu I into Ni is equal to 0, which is the equation 4, and this equation is also known as the Gibbs-Duhem equation. So what is Gibbs-Duhem equation? Summation of I d mu I into Ni is equal to 0. Now on dividing the equation, on dividing by the above equation number 4 by total mole numbers in terms of mole fraction, so we get the equation in terms of mole fractions. So this is the other type of the Gibbs-Duhem equation, right? Summation I d mu I into xi is equal to 0, right? So xi is equal to ni upon n. For binary solution containing two components, we can write above equation, which is the summation of I d mu I xi is equal to 0. We can write in terms of, if we take the binary mixture, we can write down here d mu 1 into x1 plus d mu 2 into x2 is equal to 0. Right? Now, you know that summation of mole fraction is equal to 1. So here we take in consideration the binary system. So x1 plus x2 is equal to 1. Then if we derivate this equation, then what we get, dx1 plus dx2 is equal to 0. That you can see on screen. dx1 plus dx2 is equal to 0. So now I move the one component at the left at the right hand side. So I get dx1 is equal to minus dx2. So we use this relationship in our equation. So what is our equation? D mu 1 x1 plus d mu 2 x2 is equal to 0. That we have written for the binary mixture. Now we put the we take the one component at the left hand side or right hand side, then you put the dx1 is equal to minus dx2. So you finally get this second form of the equation, d mu 1 x1 upon dx1 is equal to d mu 2 x2 upon dx2. Right? Now we know that for a solution of component I, the chemical potential expressed in terms of fugacity. So here is the equation, d mu 1 is equal to RTD ln F1 d mu 2 RTD ln F2 RTD is, so we can write down the equation in terms of F1 or say in terms of fugacity from above equations. So RTD is equal to ln F1 x1 upon dx1 is equal to RTD ln F2 x2 upon dx2. So you can see that we have written the Gibbs-Duhem equation in terms of fugacity. Right? Now you know that fugacity is directly proportional to activity, or you can say activity is directly proportional to fugacity based on the equation, equation of the activity. Right? So I can replace the fugacity with the activity term. Right? So d ln f1 into x1 upon dx1 is equal to d ln a2 into x2 upon dx2. So here you can see that we have written the Gibbs-Duhem equation in terms of activity. Right? Applying in above equation, if we want to write in terms of activity coefficient, so we have to apply the equation activity is equal to activity coefficient into mole fraction. You can see in screen A1 is equal to gamma 1 into x1. So I have placed the value of activity in the above Gibbs-Duhem equation. So is equation number 6. So you can get d ln gamma 1 x1 into x1 upon dx1 is equal to d ln gamma 2 x2 into x2 upon dx2. Now you can see there is a gamma 1 into x1 is connected with ln. So if we want to separate it, the multiplication will separate it in terms of summation because there is a ln. So and here the last x1 will be remain as it is. So we have taken it further. So x1 into d ln gamma 1 upon dx1 plus x1 into d ln x1 upon dx1 is equal to x2 d ln gamma 2 upon dx2 plus x2 d ln x2 upon dx2. Right? So now you can see that there is the terms x2 d ln x2 and that will be cancelled out because if you put the relation which have we derived further, so that both the term will be cancelled out. So finally what we get, x1 d ln gamma 1 upon dx1 is equal to x2 d ln gamma 2 dx2. Right? So it is the Gibbs-Duhem equation. The last equation, it is the Gibbs-Duhem equation in terms of activity coefficient. Now what is the application of the Gibbs-Duhem equation? Gibbs-Duhem equation is helpful in calculating partial molar properties of a binary mixture by measuring the composition of the mixture, which depends upon the total molar quantity. So you already seen it that we taken in the consideration N1 and N2, and with respect to total molar quantity, which is N, the total number of mole in the mixture. So this Gibbs-Duhem equation is very useful for calculating partial molar quantities, right? Gibbs-Duhem equation is helpful in calculating partial vapor pressures by calculating total vapor pressure. All these calculations require curve-fitting procedures. Using tabulated experimental data, the accuracy of the calculated quantity was found to be comparable with the accuracy of the original experimental data. Right? So you can use this equation for the checking of the accuracy of the original experimental data in terms of vapor pressure. Right? So these are the application of the Gibbs-Duhem equation. Thank you.